Everybody is ready? Okay. So today we will discuss um, a paradox in mathematics that is quite old, but using the knowledge of the lab, we can give some interesting answer to it. So let's first see what it is. So usually what we use in the lab, and we say we have a prior, we have some information, and then we use these marginalization rules to get our posterior belief. And in mathematics, it look like this conditional probability theory. But in practice, it is not, because in conditional probability theory, the conditional event A have to be positive. But when I conditionalize on observing an event, actually this event is always have a zero probability. When I say, well, I observe Y of Gaussian distribution, usually when we do that in our model, it has a zero probability. And you could say, well, I don't care because these rules works well, these marginalization rules work well, but actually in some very naive example, it does not work well. Like you have like a lot of issues. And this is what we will see today, like the paradox is where these rules does not work. So how we will proceed? We will first like go through a probability example with a story on how to process information, but on a very intuitive approach to see how we will define the prior and the posterior just by thinking about it together. Then we will use both base rule with the marginalization rules in what we do in the lab, and we will compare our intuition to the marginalization rules that we use in the lab. And according to that, we will see if we can fix the unmatch between our intuition and the marginalization rules. So let's imagine you are Willem, the king, and you are in your office and you receive a call. So from the NASA tells you, well, there is an asteroid going down on Earth. You kind of worried, but you need to do a speech to your people. So you need to give them a probability of the Netherlands like being shut down by the asteroid, right?
One.
So this is our goal, giving the probability of the asteroid going down on Earth, not going down on Earth, but going down on the Netherlands. So let's try to do that. If you guys have some idea, how would you define this probability of the asteroid shooting down on the Netherlands?
The size of the Netherlands as a ratio to the size of the Earth.
Exactly. That is my point.
Direction.
Sorry?
It's heading velocity.
Would you use the direction of the impact? Yeah, it's a good point. But let's say that I have no more information than just the call that I received from the NASA. I did not receive, like, for instance, the direction, the speed, or this kind of stuff. So simply, the intuition is there. For instance, if Russia is bigger, there is a bigger probability to be on to fall down on Russia, and rather than on the Netherlands because it's small, as she said. And when basically for instance, these two states are very close area, I need to especially compare the size and say, well, this is bigger, so I will use this formula. This is how intuition gives you a prior, right? So my prior probability is just this area formula. Now back on the office, I receive a new call. They're saying, well, this asteroid will fall down on a specific meridian. So the meridian is the great circle on from North Pole to South Pole. And saying, well, this is the meridian of Eindhoven. So now I need to update my belief, update my probability to give a better speech to the people. And just for a little reminder, and this is, so the meridian are this North Pole, South Pole, are this cycle, and the other one are the parallel. In those sense, just for you to know what we're talking about. So in these cases, I will compare the length, right? Are you guys convinced by that?
Yeah, makes sense.
Yeah, makes sense?
So we have the entire length of the entire meridian and
Mhm.
just take this country.
Exactly. Typically, like if I compare like the 5 meridian in France and the Netherlands, because it's smaller in the Netherlands, I will have a smaller probability to fall down on the Netherlands rather than fall down on France. Are you guys convinced by this situation? You? Yes?
I get the length argument. What is B again? Sorry.
B is like any surface on Earth. But if your question, what is the probability fall down on surface B, according to this information that it will fall down on the meridian, I will use the length of intersection between the meridian and B, and compare to the length of the full meridian. It's just
The probability of falling at B.
at B, exactly.
And this is our posterior.
Exactly. And this is our posterior belief. So there we get prior and posterior, but just by intuition, right? And it seems that most of you seems convinced by that. So in terms of information processing theory, it will give us prior, information, posterior. But now that, okay, this is just intuition, in our lab we have rules, base rules, and let's apply it, because well, intuition is fun, but when we have good theory, why not using it? So to use it, we need to define this Pxy that I showed at the beginning, the distribution. So I need to parameterize my surface according to classical, like everybody might have already seen this parameterization, lambda phi, and give a distribution.
Yeah, spherical coordinates, basically.
Spherical coordinate, exactly. Yeah. Thanks. So usually, if I want a uniform distribution, so meaning that the probability is proportional to the area, I take that, this distribution, P of lambda phi. And this is exactly equal to our initial supposition around the area, surface of area. This is exactly equal. Like mathematically, this is our intuition, but with parametrization. And then with parametrization, we can use our usual rules where we just integrate over the space over the lambda and d phi, what we do in the lab. Now let's model the information. The information is falling down on a specific meridian, so falling down on a specific lambda. So lambda, I said lambda 5. So now let's use the marginalization rules. So this is the marginalization rules. So I just do the integration over at lambda fixed and I integrate over all the phi. Are you guys convinced that this is the usual rule here, right? But I obtain 1 over 2 cos phi. And this 1 over 2 cos phi does not give me the usual results, your intuition or intuition results.
What does it give? So
it gives an additional cos phi. And this cos phi will do the fact that the length in the north will be way smaller.
yeah, okay, makes sense.
Makes sense if you compute the area, right? But if I compute only the length in the north, is the same that in the south. To you. So
yes, but it's actually, yeah, okay. Yeah.
So it's true that it makes sense when I'm computing, for instance, as you see, the area here, I need to add this cos phi to count for the fact that the area here is smaller than the area in the middle. But when I'm discussing only the length in terms of the meridian, the cos phi is now an issue, right? It's a bit as you want. So what do you guys think? Yeah.
Well, one thing I think is your asteroid is not infinitesimally thin, and so you are in fact landing on a meridian of, I don't know, a meter wide or something.
Yeah,
And
but
so now you are talking about areas again.
I don't think
Maybe.
yeah, it's not the point, right?
No, I think there is an intuition actually indeed. So if you start adding delta to this 5 degrees, right? So closer to the poles, those deltas would have more impact than closer to the
Yes. Yes.
center of Earth.
It's basically from where cos phi coming from.
Yes.
That's why the
So I think that's
cos
what
phi.
Alex is trying to say.
Yeah.
Yeah.
I was getting that.
Okay.
Yeah, but this explains when I'm measuring a surface. But now, if I just discuss the line, the specific line, this argument does not work anymore, right? If I just say that asteroid fall down on a line. And so my question to you is, for you, the right answer would be the one giving by the strict application of Bayes' rule, or the one giving by our intuition at the beginning? Bayes' rule for you?
I do think Bayes' rule, but I mean, once you know, I think it makes more sense.
Okay, Bayes' rule for you? Bayes' rule is it, everyone? Let me show you something. So this is the parametrization, but I could just switch the parametrization, right? I could just do 45-degree rotation, take lambda in this sense, and phi in the other sense, just switch.
So you move the pole.
Yeah, I move the pole, but only in terms of rotation. I don't move the Earth itself. You see? And if I do that, it's just in the case of, let's say, it's a bit like, let's say that it's like the equator is the 5-degree line. And if I do that, now I get my formula because cos phi disappears. Because cos phi now is on the other side of the measurement. But I still using the correct way of using Bayes' rule in these cases too.
Bayes' rule is not invariant for coordinate systems.
Exactly. Exactly. This is what we understand. And you see that
Application of delta Bayes rule. If you have areas, it will be invariant.
and this is where the issue is, right? Because you told me, well, Bayes' rule is better, but actually Bayes' rule can also give you the intuition just by changing the parametrization.
And if you would use instead of the point, information, if you would use a range, it would be the same.
A range?
Yeah.
Yeah, so we can show with the range, the probability of the event will be positive according to the prior, and it will fall down to the classical conditional rules, and you will have no issue. For instance, if you use range, let me. If you use range, you will have P of A positive, and this formula works well. It will be invariant of the parameterization. Everything will be fine. But most of us, when we do Bayesian rules, we use this. We don't use range. So through this example, we see that there is a kind of an issue in our process, and this is the paradox. And what I propose is to solve this. So there is something missing, right, in the formula. And from our intuition, what do you guys think is missing in this rule?
Measurement noise?
Measurement noise, it could be something, but what type of measurement? Yeah, but what is this delta?
Zero mean noise, so it gives area to your measurement.
In some sense, yes, it's a good
You want
point.
the limit of this delta going to zero to be the exact marginalization.
Yes, these 2 points. These 2 points. But when you do a limit, if we discuss area, we discuss length, and to define a limit, we need a specific geometry. So we need a limit process, as you with noise, as you said, and geometry. This is basically you just give me the answer. You just solve the paradox. But we need a way to define now this limit because we said a limit, but limit of what and what type of noise, and just to see how we can do that. So now this Willem in the office is fucked because there is like, well, Bayes' rule is broken, please help. And he's calling Bert from vacation. Bert in Cancun, and it's like, well, even in Cancun, Bert can go ahead and say, use the maximum entropy, it's way more robust. And this is what we will use for this process, noise, and these limits. So this is a formula that we propose with Nicola, is to use the geometry, the distance, and this is the margination rules, but also we add this the geometry's constraint. So basically, if this equals 0, it means that this equals 0 or this equals 0. And when the distance, when x is not in A, it means this would be positive, so this has to be a 0. So intuition-wise, this means that Q must be equal to 0 when x is not in A. It's just a way to say I take for support just A, right?
So it is minimum distance, or like.
Yeah, it's the minimum distance between x and A.
Yeah.
Just intuition, just the intuition, right? And the issue is that this mathematically is not defined. That's why we use the limit process with the noise that was proposed by Barder and Alex. And we use this noise constraint, and we just say that the noise constraint goes to 0. Good job, guys. Yeah, good job. You see, you guys all solve by yourself the problem, right? This is cool. Like you don't need me. And if we use this definition that is based on max entropy principle, and
So you literally again, you basically try all possible Qs.
so
Essentially.
exactly, I'm trying all possible Qs.
And then if it converges, then you get your.
Yes. So if the fact is, in most cases, we prove that it converge, but with all the possible Qs that are like marginal, and also this is a bit like saying that the variance around A is very small, so like the measure outside of A is almost instant. And I'm just making that sharper and sharper over the time, over the limit.
And how would you choose D?
And this is the good question. Yeah, that's you get the question. Is how to choose D? Because and the answer is let's choose the D that was following our initial intuition. So our initial intuition, we talk about the how to measure length on the sphere. So actually, a length of the sphere is the distance defined by the geodesics in geometry. And it looks like this, just D between P and Q is the
Arc
graph.
length.
Exactly, the arc length. So we choose D according to our intuition. And if we choose D according to intuition, these rules give us what we want. So we can see that with this formula, we have a way to define Bayes' rule that is standard, but follow our intuition. And this is what we want. And but you ask me, well, but then where is the marginalization rules? And actually, if we choose another distance, typically the Euclidean distance, which is not the appropriate one for these cases, I will obtain the marginalization rules and obtain these weird results that we got at the beginning. So yes, we are happy, and thanks to Nicolas for the work and my supervisor, and thanks to you guys for your attention. Any question?
Do we become the maximum entropy intelligent agent? Something left?
Yeah, it's a good question.
Information geometry. Information geometry agent.
Good luck.
It's a good presentation. Like, analogy is really, really good.
You like it? Thanks.
I really like the analogy.
Thanks. I appreciate it. The goal it was, do you guys understood what was going on? Super clear? Nice.
Can you make some kind of a statement, like along the lines, if this formula gives the same answer for all possible distances, then does it mean something? Or
Whoa.
so now we know that on sphere you actually can get different answers
Yes.
depending on the distance.
Yeah.
My question is, if there is a geometry that gives the same answer
Geometries. Yeah, D define
for all
geometry, right?
possible distances, you can imagine, does it mean something or not?
You mean I change the geometry and obtain the same result?
Yes.
It's an interesting point. What we actually prove is that if the geometry are equivalent, like in terms of if there is an isometry, you get the same result. But we don't know is that if the geometry are different, I will obtain the same result. This is how to guess beforehand. And so don't know. I cannot.
The thing you're saying is if the event you're conditioning on is positive measure, then it's always Bayesian.
Yeah, it's always based on the classical one. But if it's measure null, you need to add this notion of geometry. And if you consider two different geometry, it's hard to figure out if yes or no you will end up with the same base rule. Okay.
No, that's I understand. I was just more thinking, can you call some problem nice? If doesn't matter what kind of geometry you choose, you get the same base.
Ah.
If you follow the whatever.
Yeah, if you have formative measure, yeah. Exactly. And yeah, so I'm sorry, no, the other
Yeah,
sense.
in some sense, I don't think so, because there is always a trivial geometry where all points are separated. Something like distance between me and everyone else is always one.
Yeah.
And if your geometry gives the same result with this geometry, it means, in my intuition says that it means that your space is discrete. But if your space is discrete, it would mean at the start that probability measure of your event was positive.
Yeah.
Then you don't have this limiting property at all.
Yeah.
You can always come up with a geometry where this limiting property doesn't hold up.
Yeah, and also in the paper, we do not provide necessary condition for this process to converge.
Yeah,
Just showing that this process converge for some d's.
But you can come up with these that will never converge.
Yes.
Yeah,
That's just your problem, right? So I don't think there are problems where sort of this property is well behaved because you can construct weird metric spaces where that won't converge.
Yeah.
And then basically your thing says if it converges, it's an extension of Bayes' rule.
Yes. Yes.
We can always come up with things.
Yeah, where distance is a hyperparameter which you need to select.
Yes.
And it's your
Yeah.
You muted? Oh, okay, but I cannot see actually.
No one raised there.
No one raised? Okay, so it's done. So if you, just a small bonus because we are fast. So actually, if we choose like the distance on the map, the one that just I take a roller and measure stuff, the distance is this one, the Euclidean one, but on the parameter.
Is this on Mercator
projection or in
Exactly, I project the Earth,
Okay.
and this classically all guys know that it makes the north way bigger than the middle, and this is where when the cos phi appear. And actually, with this, the rules that we proposed earlier actually give you the cos phi parameter. Yeah, so that was the small bonus for the end, and thanks for your attention and your time.
I remember I spent like very lot of time
Yeah.
to push ticks to produce it. No. It was not Opus yet, it was paper written 2 years ago, right?
Okay. No Opus yet. Difficult time.
Yeah.
Nice.
Really nice presentation.
Yeah.
Good job.
Thanks. Yep.